Now let's do something different. Let's take our transmission line, our length of transmission line, and instead of attaching a load at one end, at the end of the transmission line, let's attach a source at the beginning. And of course, this source is simply an equivalent for some elegant and complicated and beautiful piece of electrical engineering that is supplying energy into our transmission line. And if it's linear time invariant and we're using time harmonic sources, signals, then we can represent this as its Thevenin's equivalent. Again, this is not a physical representation of what's true. It's simply an equivalent circuit. And of course, this allows us to simplify our analysis. We could go through and try to figure out how does this impact our 6 fundamental functions of a transmission line: voltage, current, impedance, or plus voltage, minus voltage, reflection coefficient. We could rewrite them in terms of the parameters of this source, VG and ZG. Now we do this in EECS 723, but we're not going to do that here. Instead, we're going to view this length of transmission line as a source transformer. And we're going to ask ourselves, what is the equivalent source now of this entire circuit? Notice what we have once we took a source and connect a 2-port device, in this case a transmission line, to it. We have a new source, a new equivalent source, a 1-port device. A new equivalent source with an output voltage, or V out, and output impedance, Z out. And the question is, what are those values and how do they relate to the parameters of this circuit, specifically VG, ZG, Z0, beta, and length L of this transmission line. This shows this transformation, the idea that our 2-port device, or length of transmission line, is a source transformer. We start with the original source and it transforms into a new source, the equivalent circuit for the transmission line and the original source together. This new equivalent circuit has a value V out and Z out. And what are those values? One thing we can say about it almost certainly is that the new voltage source V out will be different than the original source VG. Likewise, the new output source voltage, the source voltage Z out, will be different than the original source voltage ZG. But what are the relationships between these values? I hope that you recall from an earlier presentation that we went through and examined the case where we put a 2-port device and we know the transimpedance parameters of those 2-port device, the impedance matrix consisting of 4 values. And from that, we were able to determine the transformed source in terms of VG, ZG, and these 4 transimpedance parameters. And for this case, we see that this 2-port device transforms the original source into a new source with a voltage, open circuit voltage V out, and source impedance Z out. In terms of the parameters, the 6 parameters, the transimpedance parameters in VG, V out here and Z out here. So the question is, how does this help us with the transmission line? In order to use this to determine the transformed source, we need to know the transimpedance parameters of a transmission line. And of course, thus far, we have not examined that or thought about that or presented what are the transimpedance parameters. The transmission line is a 2-port device. Every linear time invariant 2-port device has an impedance matrix. What is the impedance matrix of a transmission line, the length of transmission line? I suppose we could Google the impedance matrix of a length of transmission line, but we don't need to. Remember, we know how to determine the transimpedance parameters of a 2-port device. We know the procedure, the experiment that we have to go through. In this case, we do a schematic experiment, and because we know and understand the results of the telegrapher equations, we can easily determine those transimpedance parameters. So let's do that now. First thing we do, of course, is put an open circuit on port 2. By doing so, we make I2 equal to 0, and I should have said explicitly I2 is equal to 0 here. So we only have one current going into our 2-port device, and that is at current I1. And what we want to do is determine then the resulting voltage V1 and V2. In other words, we're going to determine the voltage at port 1 due to the current at port 1, and likewise the voltage at V2 due to the current at I1, and I1 only since I2 is equal to 0. So how do we determine that? Well, By KVL, we know V1 is the voltage here at the beginning of the transmission line, and V2 is the voltage at the end of the transmission line. And for this circuit, we can determine the voltage at everywhere on the transmission line, and from that solution, determine the voltage at either end. So let's do that. First thing we need to do is calculate the load reflection coefficient. And you may say, what load reflection coefficient? We have no load. Well, we do have a load. It's an open circuit. On port 2, we've connected nothing. Open circuit. That is an impedance of infinity, and we can calculate the resulting reflection coefficient, load reflection coefficient for an open circuit. So we take the definition of gamma L, and in the place of ZL, we put infinity. A little bit nebulous what a complex number infinity is. It's any complex number whose magnitude has a value of infinity. And in this case, what we find then is the ratio of infinity to infinity, we can say, is equal to 1. Gamma L is equal to plus 1 times e to the j0 for a open circuit, an impedance whose magnitude is equal to infinity. So we can insert that into our solutions for the total voltage of a terminated transmission line, where the transmission line is terminated now in a load reflection coefficient of gamma L. Likewise for total current in terms of gamma L. Gamma L is equal to 1 here, and so this is the result we get for voltage, total voltage, and total current. And of course, we're adding together two complex exponentials, one e to the minus j beta z, e to the 1 is the plus j beta z. Here we're taking the difference of the two. And of course, we can use Euler's equation then to simplify these results. And we get this result here. In this case, a result in terms of cosine beta z, and this in terms of sine beta z. So we're almost done here. We have the total voltage and total current at every place on the transmission line. And since we know the total voltage and total current everywhere on the transmission line, we certainly know the total voltage and total current at each end of the transmission line. And that's what we need to determine the transimpedance parameters. We take our total voltage expression and we evaluate it at the beginning of the line at z is equal to minus L. Insert minus L where we had z, and this is the result. This is a complex number, which is equal to the voltage now, V1. And actually, this should be V1. I just noticed I have a typo here. I1 and V1 at port 1. That should be V1.
You're wasting our time, Earth creature.
I1, the current here, and that's correctly written as I1, we simply take the total current and we evaluate it, again, at this position index z is equal to minus L, and we have this result. Let's go to V2, the open circuit voltage here at the other port V2. Remember, I2 is equal to 0 here, so let's determine the voltage V2. We take our total voltage expression and now evaluate it at the specific location index of z is equal to 0, and we get this result. From these three complex values, we can determine two of our transimpedance parameters. Our first transimpedance parameter, Z11, is equal to the voltage at V1 divided by the current at I1 for the explicit condition where the current at I2 is equal to 0. In other words, the port 2 is an open circuit, and that's what we've analyzed. And so we can take those results and take the ratio and find this is the value of Z11. Z21 is now the ratio of the voltage at port 2 to the current at I1, again, only when the current at I2 is equal to 0, only when port 2 is terminated in an open circuit, which it is in our case, and these are the results we got, and therefore this is the value of Z21. All right, of course, there are two more transimpedance parameters we need to find. We need to find Z22 and we need to find Z12. We could go through and then change the open circuit to port 1 and do the whole thing over again. But remember, the transmission line is a symmetric circuit. If we take it and we flip it around, we still have the same circuit. So we're going to go through and take advantage of the symmetry of the structure. We see that if we go through and do the second analysis with an open circuit at port 1, effectively it's the same circuit as what we analyzed before, only rotated around. And therefore we're going to get the same results as we did in the first situation here. In other words, we find that Z22 is equal to Z11 by the symmetry of the transmission line. Likewise, due to the symmetry and reciprocity, we find that Z12 will be equal to Z21. And so if we look at our complete impedance matrix of a length of transmission line, a length of transmission line L is our lossless transmission line, of course, this is the resulting impedance matrix. There are several things to note with this result. First of all, we note that the transimpedance parameters depend on the parameters of the transmission line. There are three parameters that characterize a length of transmission line. The characteristic impedance Z0, which is in each of the four transimpedance parameters. The spatial frequency beta for the transmission line, which again is in each of the four values. And likewise, the physical length of the transmission line L, which we see in each of the four values. We look at each of the results and we see they have units of impedance, all right, because the units of Z0 is ohms. The resulting transimpedance parameters have units of impedance. So that's a sanity check that makes it feel better that we have the right answer. Finally, we look at each of these four parameters and we see that they are purely imaginary. The real part of each of these four is equal to 0. This should not surprise us at all. In fact, if we got anything different than that, we would know that we had the wrong answer. Because we know that if we have a lossless two-port network, like a lossless transmission line or length of lossless transmission line, the transimpedance parameters then must be purely imaginary. Every lossless two-port device has imaginary transimpedance parameters, and this is the result that we get. Now, think about the ways we've characterized a transmission line. We have the characteristic impedance of a transmission line. That is a characteristic of the transmission line, a real value of Z0. Notice that none of the transimpedance parameters is equal to that characteristic impedance, Z0. In fact, it can't be because each of the transimpedance parameters must be purely imaginary, whereas Z0 is purely real. What about the input impedance? Well, again, as I state very often, a transmission line, a length of transmission line, has no input impedance. A length of transmission line terminating some load has an input impedance, but a two-port device does not have an input impedance. A two-port device has transimpedance parameters. We terminate the transmission line in some load, and then yes, we can determine the input impedance, but that input impedance depends on the load itself, and so we can't describe an input impedance of a transmission line, only the input impedance of a transmission line when terminated with some arbitrary load ZL, and it will depend on that load ZL. So let's take our transimpedance parameters for a length of transmission line and insert it into our solution for a two-port device that transforms an original source into a new source. Since we have the impedance matrix, we can insert them in these results, and this is what we get. This is the new open circuit voltage for our transform source. Notice it has the right units. This is a coefficient, and we have units of voltage. Notice it depends on all of the parameters of our circuit. The parameters of the transmission line, Z0 and beta and L. Likewise, the voltage source of the original source and the source impedance of the original source. True for V out and for Z out. Now, what do we use this for? Do we write this down? We're certain that at some point in the class we're going to have to calculate what these values are. It turns out no. I just wanted to go through and calculate the general expression and show that these are plausible results. They pass the sanity check. They have the right units. They involve all of the elements of the circuit itself. We're not going to use it to solve general problems, but we are going to go through and consider this result to evaluate a special case. We're going to go through and insert a special case in here, and we'll find that the results simplify dramatically. So one thing we can determine from our result is that V out is almost certainly going to be very different than the original open circuit voltage VG. Likewise, Z out is going to be very different than the original source impedance ZG. Our length of transmission line has transformed our original source very fundamentally, that we have different voltages, open circuit voltages, and source impedances after that transformation. We might ask ourselves then, what about the available power? What is the relationship between the available power of the original source and the available power of the transformed source? We could go through and do analysis and try to figure that out, but we don't need to do that because we know that our lossless two-port transmission line, our lossless transmission line rather, is lossless. It's a lossless two-port device. And a lossless two-port device, as we've shown before, cannot alter the available power. When it does a transformation of the source, it will change the original open circuit voltage to a different open circuit voltage. It will change the original source impedance to a different source impedance. But the one thing a lossless two-port device cannot do is alter the available power. The available power of the original source must be equal to the available power then of the transformed source, or vice versa. Actually, the available power of the transformed source is equal to that of the original. The length of transmission line cannot alter that value. All right, everything we've done thus far really leads up to this point, a special case. We're going to look at a special source. And in this case, the special source has a source impedance, an original source has a source impedance that is numerically equal to the characteristic impedance of the transmission line. ZG is purely real, with the real part equal to the characteristic impedance Z0, and imaginary part is equal to 0. In other words, we have a source whose source impedance is a resistor that is numerically equal to Z0. Once again, I say numerically equal to Z0. I don't want to infer that somehow the source impedance and the characteristic impedance are in any way an equivalent physical parameter. They just happen to have the same numerical value in this case. If our source has a source impedance numerically equal to the characteristic impedance to which it is attached, we call that source a matched source. Once again, don't infer that a matched source has anything to do with a conjugate match. A common mistake that we have. When we say we have a matched source, students will say, oh, a matched source, that means we have a conjugate match, but that is not the case. A matched source only means that we have a source numerically equal to the characteristic impedance that it's attached to. As I stated before with a matched load, we can't say anything about a conjugate match. A conjugate match is when we have a source impedance and a load impedance that are related by complex conjugates. To determine that, we need to have both a source and a load. If we look at this circuit, we have a source, an equivalent source. We have no load. We cannot infer or determine whether we have a conjugate match at all. All we can say is that this source is numerically equal to this characteristic impedance. In that case, we say it is a matched source. I don't know if we have a conjugate match or not. We may or may not. Again, two different things. Even though we use the same word matched for a conjugate match or a matched source, the physical ramifications are completely different. They don't mean the same thing. I always tell students this is like in English we use the words there, or there. They sound the same, but of course they mean different things. Or two, and two. Same sounds, but very much different words and different meanings. And that's what we have here. I use matched for conjugate matched, or matched for matched source, or matched for matched load. All three have different physical ramifications, different physical meanings. Make sure you don't confuse those. We take then the results we had for the transimpedance parameters of a lossless two-port device and the transformation of that source from our original source to a new source. And now we drop in the situation where the original source impedance ZG is equal to Z0. We diligently do all the algebra and we go through and try to figure out what is the new transformed open circuit voltage V out and the new transformed source impedance Z out. And when we do that, we find many things drop away, cancel with each other, and our otherwise complex, very difficult mathematical expression simplifies dramatically, simplifies greatly. In fact, what we find is when we have our special case, when our source, our original source, has a source impedance which is numerically equal to Z0, we find that the transformed source now will have a source impedance which is also equal numerically to Z0. What about the transformed open circuit voltage source? Is it equal to VG? Well, almost. What we find is now our transformed source is equal to our original open circuit source voltage VG times e to the minus beta L. basically we have a phase shift now of that transform source, a phase shift that is equal to the electrical length beta L of that transmission line. Notice the magnitude of our transform source V out and the magnitude of original source VG are equal to each other. The phase is different, again, by a value of beta L, just a phase shift there. And so what we find when we have a matched source, this very special case, that the transform source now is very much related to the original source. It has a source value, a source impedance numerically equal to Z0. So this is a very special case. The most important thing about this is all true regardless of line length. The transformation, if you look at this now, there is going to be the same regardless of the transmission line length, or more specifically, the output impedance Z out will be equal to Z0 regardless of the transmission line length. So we see this is very similar to what we had for a quote-unquote matched load. In a matched load, we see that our lossless transmission line transforms our load numerically equal to Z0 into an input impedance, which is likewise equal to Z0. And this is true regardless of the length of the transmission line. If we have a matched source, our transmission line will transform that source impedance of Z0 into a new source whose impedance is likewise equal to Z0, and that is true regardless of the length of the transmission line. So whether we have a source, a matched source, or a matched load, the transformation of the length of transmission line will be one that does not alter the load impedance or source impedance in that transformation if that source or load impedance is quote-unquote matched, meaning it is numerically equal to Z0. By the way, I may not have mentioned this, but that does not mean we have a conjugate match. Again, we cannot imply or infer anything about whether we have a conjugate match or not by the statement the load is a quote matched load or the source is a matched source. All we can say from that is something about the source or something about the load. To determine whether we have a conjugate match or not, we have to say something about the source and the load. And in neither case, with the special case where we had a matched load, nor in this case where we have a matched source, have we said anything about the other part of the circuit that is necessary to determine whether a conjugate match exists. We might have a conjugate match with a matched source, or we might not. We might have a conjugate match with a matched load, or we might not. Again, we have to complete the circuit before we can determine whether we have a conjugate match. It is completely independent of whether we quote-unquote have a matched load numerically equal to Z0 or a matched source whose source impedance is numerically equal to Z0. Do not make that mistake.